Can you leave it up?
I can. In fact, I can leave it up for me to. Okay, then I said that homework, it's disjointed. That's why I really wanted you to focus on actually getting it done. If you didn't get it done, you need to get it done. It's disjointed from the rest. This is like the only time we really get to just focus on that one subject. So do it as you're still kind of fresh in your mind of coming up with the lesson. I know it was last week, but you can rewatch the video. It really just comes down to that one problem we did that you just find. I'm sure we'll do one in class. I'm sure we'll have questions about it. But it really is finding a Pythagorean identity that goes from one to the other. So if I'm given sine and I need to find cosine, I use sine squared plus cosine squared equals 1. That will get me from one to the other. All right, so if there's no questions about work, then let's go over homework questions that we might have from that, what I just brought up, I guess. Yeah, go ahead. Number 3, yeah. Number 3, we shouldn't have had too many questions on it. It was just the fact that I didn't put the answer on there. I just put what the answers were, which means that you need to take a step. So the first thing I'm going to look at on number 3, well, let's just write it out. It's asking me, okay, you're given the cotangent alpha of something, and they also tell you, well, negative pi over 2 is less than alpha is less than 0. If you don't understand what's going on here, you can still do the bulk of the problem. All this tells you is whether you're positive or negative for those given things. This is just describing what quadrant are you in to tell you what's positive or negative. So if I picture negative pi over 2 to 0, negative pi over 2 is actually straight down. It occupies the same space as 3 pi over 2. It would just be, because you could picture if I went positive pi over 2, I'd be up here. But it asked for negative pi over 2, so I'd be going the opposite direction. I'd be down here. And then it goes to 0. So they're saying this angle is somewhere in quadrant 4. We're in quadrant 4. I'm going to erase this real quick. We are in quadrant 4. That's all this is really telling me, that this is quadrant 4. And then we just go, okay, all students take calculus. So I'm just going to write what's positive. Everything else is going to be negative. So in quadrant 4, we should have cosine is positive. And we should also say its buddy secant is also positive. But if you didn't get this, you'd still be able to get most of the problem done. This is just telling you whether you put a positive or a negative in front. That's just a small aspect of the problem. The big problem is getting the values. So if you're ever stuck on this on a test, don't let it bog you down. Just go, okay, I know cotangent alpha equals 1/3, and I need to find the other trig functions using identities. Well, the very first identity you should use is, if I give you cotangent, you should immediately go tangent. Thank you. Tangent is going to be flip the fraction. That would be 3 over 1. Yeah?
Oh, that's actually negative 1/3.
It's negative 1/3. Thank you. Which makes sense because we're in quadrant 4, so they'd all have to be negatives except for cosine and secant. Yeah, so we'd have tangent alpha equals a negative 3 over 1 or just negative 3. I don't care. You can leave it as negative 3 over 1. Some people see that better as having the fractions. I'd probably write negative 3, but negative 3 over 1 is awesome. That's it. We got one of our trig identities. If you can't do that one, you're just not doing the work in the homework, because that's all it is. If I give you cotangent, flip it, you have tangent. All right, now the next thing is we need to find all of the other ones. So I'm going to look at cotangent. I'm given cotangent. And I'm telling you right now, we're going to have to use a Pythagorean identity, because Pythagorean identities are the only ones that go from one to another trig thing. So I picture ones that use cotangent. So we'd go to our sheet, or we'd hopefully starting to have this memorized, that 1 plus cotangent squared alpha would equal, is it cotangent cosecant, or is it cotangent secant squared?
Cotangent secant.
Cotangent secant?
Yeah.
We sure of that?
Oh, wait, no.
Cotangent goes with secant?
I mean cosecant.
Cosecant, yes. Cotangent goes with cosecant. Cotangent goes with cosecant. So we're going to have cotangent squared. It equals this cosecant squared alpha. Now, we already know cotangent is negative 1/3, so we're going to take that 1/3, negative 1/3, And we're going to plug it in for cotangent alpha. That's going to give me 1 plus. Now remember, you're replacing the entire cotangent with it. So no more writing cotangent. In its place, we write negative 1 over 3. But that's squared. Don't forget about the squared. And that's going to equal cosecant squared alpha. All right, here's my little pro tip. I'm going to square this first before I rewrite 1, because 1's really easy to rewrite with a common denominator. So if I square negative 1/3, we know a negative times a negative equals a positive. So we're going to have a positive 1 squared, which is 1, over 3 squared, which is 9. Now, in the place of 1, I'm going to write 9 over 9. And that's going to equal our cosecant squared alpha. Good so far? Any questions so far? Really, this is just plug and chug. That's why you just do it for a day. It's just plug something in and chug your way out to get your solution. All right, so now we have a 9 plus 1 over 9, which is going to be 10 over 9. Yeah.
Where did we get the 9 over 9?
I just went ahead and so this is really just 1.
Yeah.
You can't do 1 plus 1 over 9 because it doesn't have a common denominator. So what I do is I change 1 into 9 over 9 so that I can do this addition.
You can just do that?
Yeah.
Oh, okay.
That's why if you look at my logic, I do the square first. I come up with the 1 over 9. And I think about how I can rewrite the 1 so I don't have to do another step. Because otherwise I have a 1 plus 1 over 9. I have to do another step where I make it 9 over 9. Why can't I do it all at once? That's why I do the squared first to let me know how to rewrite the 1.
Okay.
And the good thing is they always have 1 in them. Because we have sine squared plus cosine squared equals 1. We have 1 plus tangent squared equals secant squared. They all have the 1 in it, so they're always going to appear like that. All right, so we have 10 over 9 equals our cosecant squared alpha. We're going to take the square root of both sides. Knowing that when I take the square root, I have a positive or negative. Here might be a good point to go, okay, I know it can be positive or negative. Let's look back up here. Is this cosine? No. Is it secant? No. That means it needs to be negative. So I'm going to pick the negative version of this. Also, it can only be negative. Okay. Yep. So we can get rid of the positive and negative and say, oh, it is the negative. And we're going to go negative. Now, in our head, we're going to go, okay, if I take a square root of a fraction, I'm taking the square root of the top. Square root of 10, that's an ugly number. I'm going to leave it as square root of 10. Square root of 9, not an ugly number. Square root of 9 is just 3 equals cosecant alpha. And boom. I got another one. My next one's really, really easy because I just flip it and I have my, what goes with cosecant? Is it sine or is it cosine that goes with cosecant? It is sine. So we're going to say, okay, my next one is sine equals a negative 3 over square root of 10. We should do some simplification, but you guys can do that. Just multiply it bottom and top by square root of 10. Now, here might be my advice. So now we know sine. So if I know sine, I can use sine squared plus cosine squared equals 1. But do you remember why I might want to use this tangent value instead of sine? I talked about it last class. So we have two options. Let them put them both up there. We could use sine squared alpha plus cosine squared alpha equals 1. Or we could use the fact that 1 plus tangent squared alpha equals secant squared alpha. They will both work. If you kind of picture with me, I can take this negative 3 over 10 squared and plug it in for that sign. Or I can take this negative 3 over 1 and plug it in for the tangent. I can see two reasons for picking this one. Can anyone see any reasons why I might want to use this one versus that one? It's easier. It's just a negative 3. I have to square a negative 3, where this one I have to square a 3 over square root of 10. There's one more reason I almost will always pick the reciprocal value. And that's because what's easier to do? Flip a fraction or plug it through this equation and go all the way through it? So I'm pretty sure this is right. I'm pretty sure, because I've done this a lot, that this one's correct. But if you haven't done this a lot, I would have a lot more confidence in this -3 than this answer. And why plug something in you don't have confidence in? I'm going to plug in the one I have confidence in. Yeah. Yeah. So I'd plug in that -3, and so we would have 1 plus -3 squared equals secant squared alpha. That's going to be a real easy way to go through it. Now we just have to square 3, which is 9, 10, square root of 10. We have our secant.
What is that for? What's that finding?
It's going to find secant.
Oh, okay.
Yep, and secant will help us find cosine because we just flip it.
Okay.
I'm going to let you finish that one, though.
I don't have any more room.
You have plenty of room.
I'm gonna write that.
If you picture, this one's going to be really quick. It's just 9 plus 1 is 10. Take the square root of 10, and that's your secant. Flip it, and you have 1 over square root of 10, and you have your cosine. All right, other questions? Yeah?
So I did it a different way. I used the quotient identity for cotangent.
The quotient identity?
Yeah, like cotangent equals cosine over sine.
Yeah.
Answer for the answer.
You're going to get a different answer most of the time. Did you get the same answer?
I'm pretty sure I can check again.
If you got the same answer, so sometimes it works.
Can I check? On the key.
Are you looking for this one?
Yeah.
Did you come up with the same sign value
Yeah.
of -3 over, it would be -3 squared of 10 over 10?
Yeah.
Okay, yeah. Sometimes it works, sometimes it doesn't work. So the problem with it stems from the fact that, so you use the quotient identity. So you use the fact that maybe tangent equals sine over cosine.
The cotangent.
You use the cotangent. Okay, so we have cotangent alpha equals cosine alpha over sine. Did you use any of the Pythagorean identities?
Yeah.
Oh, okay. Oh, use this one to clean it up. Okay, that's cool. I'm okay with that.
Okay.
Okay. The times that you can't use this is you can't go, oh, you know what, cotangent, because cotangent, this one was negative, was it negative 1 over square root of 3? Or 1 over 3?
No, just 1 over
Yeah, negative 1 over 3. So you cannot say that cosine is -1 and sine is 3. That doesn't work. Because these could be different things that turn into 1/3. Kind of like 1/2 divided by 1/4 is different than 1 over 8. So you can't go directly from this, but what you did was fine because you just used it to clean it up. All right, other questions?
So you need to find the sine, cosine, tangent, and
Yes, you got to find all 5 of them.
oh, 5. Okay.
So they give you 1, and there's 5 more. So if I give you, say I give you cosine, you have to find secant, sine, cosecant, tangent, cotangent. We're not done yet. You have to finish this. This will get you secant, you flip the fraction, and you will have cosine. I just would like to have some people finish this on their own. Okay?
Did it.
Nice. And you had room?
Yeah.
Just enough.
I just squeezed it.
The nice thing is this is a pretty easy one because you don't have a fraction. Okay, other questions? Yeah.
Oh, I was just talking about this one still.
Okay, yeah.
That's fine. I'll ask you later.
No, you can ask me right now.
Oh, I was wondering if I just needed cotangent left because I could.
You already have cotangent, right? Because we started with cotangent.
Okay.
This would be our secant,
Can't.
and we'd flip it, and it would be our cosine.
Cosine. Okay.
Because this is technically square root of 10 over 1. So if you flip it, it turns to 1 over square root of 10. All right, then let's go back to what we were doing before we got this disjointed stuff. I'm telling you, you need to get this homework done. You need to get this homework done so you understand this stuff. Today we're talking more about simplifying things. I give you an equation and I ask you to simplify it. Now, the very first day we did this, all we had to do was turn things into sine and cosine, and things would just work out and be simplified. Well, we're going to get to ones that are a little more complicated, like this one. If I tell you to turn everything to sine and cosine, I already did it. But this is definitely not simple. It is not simplified. So we're going to learn 2 big rules today. One big rule, and we talked about this before. If you have 2 fractions, push the fractions together. If you have 2 fractions to simplify it, I want to push those fractions together. So I actually want to do this addition. The problem is if I want to do an addition for fractions, I have to have a common denominator. And it can't be, oh, it looks close. Close does not cut it for common denominators. They have to be exactly the same. So I need to have the same thing here as I do here. Right now I have one plus sign and I have one minus sign. Those are different. You can't do this addition. So if you remember from that first day I talked about kind of this idea. Let's say I have 1 over 3 plus 1 over 4. What do I need to do to create a common denominator? JP?
You multiply each side or each denominator.
Yeah. Other denominator? Yeah. We multiply each fraction by the other denominator. So it looks something like this, where I can have 1 over 3. Now the other denominator is a 4. So we multiply by 4 over 4. I'll put those in parentheses saying I'm adding that. To get that 4, we'd have 1 over 4, and I'd multiply that by the other denominator, which is 3 over 3. Which would then give me, 4 over 12? Plus 3 over 12, and lo and behold, I have a common denominator. Does it always work for fractions? No. I mean, it always works for fractions. It might not always be the easiest way. But we can always count on the fact that if I multiply by the other denominator, I will create a common denominator. So now we go back here. I have 1 over 1 plus sine theta. Even though it looks complicated, I'm going to multiply the entire thing by the other denominator, which is going to look something like this. So let's put our equal sign. I have my 1 over 1 plus sine, what do we have, theta? We have a theta. We're going to multiply that by the other denominator. The other denominator is 1 minus sine theta. 1 minus sine theta. Now I'll write the other fraction. The other fraction is 1 over 1 minus sine theta. Multiply by the other denominator. That's multiplying by 1 plus sine theta. All over 1 plus sine theta. Just because it doesn't look easy doesn't mean it's the wrong path to go down. This is a good fundamental idea to know that if you have two fractions that are being added or subtracted, add or subtract them. Turn them into one fraction and see what happens there. All right, let's look at the first one here. So we would multiply that top number, that 1. Remember, this 1 is actually getting distributed to both things. I know it doesn't affect anything, but we need to start looking at it that way, that 1 gets distributed to both those items. Well, 1 times 1 is 1, so we have 1. 1 times a negative sign is a negative sine theta. Here's something where we need to start getting comfortable with. I'm doing this multiplication. It's 1 plus sine theta times 1 minus sine theta. You could distribute it all. But we need to start realizing that this is a difference of squares. This is a difference of squares, and we can very quickly do these. So I'm going to do a little note off to the side. I know I've done this note before. But I'm going to note, if I ever see I have a minus b times a plus b. That means they look identical, like they do, except for a plus and a minus. Well, a minus b times a plus b is going to equal a squared minus b squared. At some point, we need to start memorizing that. So I don't want you to be on a test having to distribute this whole thing out and make mistakes. So instead, I'm going to go, okay, 1 plus sine times 1 minus sine would be a squared minus b squared. Our a is 1. So realistically, I have a 1 squared minus a sine squared theta. What's 1 squared, though?
1.
Just 1. Do you have to put the squared? No. You could just put the 1. I'm just, for my notes-wise, I'm putting that as 1 squared. So I can remind myself, oh, it's a squared minus b squared. All right. Then we'll have a big old plus sign. I will note, it's not going to appear right now, but if you picture this is a positive 1. I'm going to distribute to both things. Now, what I want to start thinking about, if this was a negative, the negative would distribute to both things. That's going to be the thing that catches people. So we really have a positive 1 being distributed to, bless you, both of these items, giving us 1 plus sine theta. All over, oh, that's 1 minus sine times 1 plus sine. That's a minus b times a plus b. So that's a squared minus b squared. So this time I didn't put the squared on 1. You do what you want to do on your notes. These are your notes. There's nothing wrong with writing 1 squared as long as it doesn't confuse you. As long as we can all at the end of the day say, yep, that's just 1. Do we have exactly the same denominator? Yeah, it's just 1 minus sine squared. We have the exact same denominator, which means we can add our numerator. So now we're going to have 1 minus sine theta plus 1 plus sine theta all over 1 minus sine squared theta. But we should see something. I have a negative sign plus a sign. That's like if I have a negative 2 plus a 2, we're just going to have 0. So these are just going to cancel out. I have a negative sign plus a sign that equals 0. I still have that 1 out front. I have that other 1, so that's going to be 2. We're going to have 2 on top. So this is going to equal 2 over 1 minus sine squared theta. That's not fully simplified. And here's that second thing I said has to start jumping out to you. Do you see that sine squared? Do you see how there's a 1 attached to it? We have to go back to that Pythagorean identity where sine squared plus cosine squared equals 1. So this is where I go off to the side and go, you know what? I know that sine squared alpha. Well, what are we using? We're using theta. Let's say sine squared theta plus cosine squared theta equals 1. I know that's true. That needs to be memorized. Sine squared plus cosine squared equals 1. I want to make this have just 1 minus sine squared. So I want to transfer this sine squared to the other side so that I have 1 minus sine squared. Well, that just means I'm going to subtract sine squared from both sides. Minus sine squared theta. And now I'll just have cosine squared theta equals 1 minus sine squared theta. Now make sure your negatives are in the right place. Do I have a positive 1? Yeah. Do I have a negative sine squared? Yeah, this matches identically to this. So that means I can replace this whole thing with cosine squared. So we can now take this cosine squared and throw it in place of all of this, which now gives me 2 over cosine squared theta. But that is not fully simplified. It's close. What can I do? I can do one more step to this. And maybe this will help. Does 1 over cosine equal anything?
Secant.
It equals secant. Yeah, so if I have 1 over cosine squared, that's going to be the exact same thing as 2 times secant squared theta. And that is now fully simplified. So what is this? This is really just a bunch of rules that we have to practice. This is just a bunch of rules that we need to practice. Our first rule is, hey, if I have 2 fractions and I'm asked to simplify it, push them together. We had another rule, difference of squares. Another rule, hey, if I have cosine on the bottom, I could probably change it to secant to get rid of that fraction. Another rule, sine squared plus cosine squared equals 1. Something we need to start looking out for when we have squares that we look for those Pythagorean identities. Questions at any of the steps I chose to do on this one? You practice this one enough and it's a really, really easy problem. You don't practice it and it's really, really tough. It just takes a little bit of practice. All right, let's learn another rule. Simplify that. Well, if I see the word simplify, based upon that first lesson we had, I change everything to sine and cosine, and I just, everything's already in terms of sine and cosine. Oh, I got the Pythagorean theorem that says sine squared plus cosine squared equals, wait a minute, this isn't sine squared. Because if this was sine squared, we would do something like this. So if I ever see a sine squared and a number 1, we start thinking about using the Pythagorean identity. Unfortunately, this is not squared. Looks really close to the other one, though, doesn't it? Like it's just a square away from it actually working. If this was 1 minus sine squared, we'd be awesome. So this leads us to another rule. If we see something like this, 1 plus sine of a number, 1 minus sine of a number. I'm going to see what notes I put in there. So I will put a little note here. Note, we need to start recognizing these items, like 1 plus or minus cosine. We should start recognizing if I see 1 plus or minus sine of a number. We should start recognizing if I see 1 plus or minus, I don't know, we could even say secant of x. Basically, if you have 1 plus or minus any one of our trig things that aren't squared, here's going to be a trick to make it into something squared. And that is multiplying by the conjugate. The conjugate is just like creating a difference of squares. So if I look here, if I have 1 plus sine theta, I'm actually multiplying by its conjugate. The conjugate would be 1 minus sine theta. 1 plus 2, the conjugate would be 1 minus 2. 1 plus table, the conjugate would be 1 minus table. You just alter that plus or minus that's between them. So if I see something like this, my thought is, hey, this is really close to being 1 minus sine squared and is what I want it to be. I'm just going to multiply by the conjugate to create that. So we're going to take that cosine squared. Looks like gamma. Maybe it's a y. Cosine squared over 1 minus sine. Might be gamma, might be y. Doesn't quite look like gamma, though. And what we're going to do is we're going to say, I want to change that denominator by multiplying it by 1 plus sine y. To get the squared. I'm creating that square. Knowing that when I square 1, 1 just stays 1. So I'm not, all I'm going to get is the square I want. Now, am I allowed to just multiply the bottom of the denominator by something? No, I have to do the top and bottom. So what goes with this goes to the top as well. So we're going to have 1 plus sine y on top. Let's do the multiplication. Here's a little advice for you. Don't distribute this, first of all. Sometimes you'll have to distribute, but most of the time you won't have to distribute this. So that top part I'm just going to leave as cosine squared y times the quantity 1 plus sine y. I won't distribute unless I have to. You'll start to know when to distribute and when not to, just based upon what we're going to do next. This is a difference of squares. So I said we have to start realizing this. This is 1 minus sine times 1 plus sine. So this is going to result in 1 squared minus sine squared y. What can I replace 1 minus sine squared with? If you're not sure, look above. What was that?
Cosine squared.
We can replace it with cosine squared. I got that from the top. Look at the problem above. I did that in the notes. Off to the side that, 1 minus sine squared equals just cosine squared. So I'm going to replace that bottom with cosine squared. Replace the bottom with cosine squared. It'll turn into 1. Yeah, just the cosine squared and the cosine squared are going to cancel out. Now, be careful here. If this was a plus between here, it's a multiplication, but if this was a plus, we couldn't do what we're about to do. If this was a plus, we'd have to write it as 2 different equations. So picture that with me real quick. If there was a plus between here, see that tiny little plus? It's not there, but just for the sake of it, we'd have to break this apart into two equations. We'd have cosine squared over cosine squared plus 1 minus sine y over cosine squared. It's not a plus, it's a multiplication. Multiplication lets me turn this into a 1. There's actually just a 1 there. So we are just left with 1 plus sine y. And surprisingly enough, that's as far as we can go. I don't have a fraction, so I can't multiply the top and bottom by 1 minus sine. We don't have a fraction, I just have a sine and a 1. We're good. Sometimes when we simplify, it just turns into 1 plus something. Questions on that? Okay, so the two things we really need to learn from this lesson. One, if I have two fractions, push them together. If they're being added or subtracted, push them together. If you see 1 plus or minus any trig that's not squared, make it squared by multiplying the top and bottom by its conjugate. You're going to know to do it because it's a fraction you can't do much with unless it was squared. That's going to be your hint. All right, now we're going to talk about this one. That was a really good one, though. This one is just like a pro tip. Doesn't happen a ton of times, but it's something nice that you can see. We have something to the 4th power. How do we deal with things that aren't squared? Squareds we know how to deal with. We find a Pythagorean identity that works for it. Our sine squared plus cosine squared equals 1. Our 1 plus tangent squared equals secant squared. Well, this is to the 4th power. We do not have anything on here that has to the 4th power. So I'm going to once again make a little note to myself. Hey, if I ever see a squared minus b squared, I can always rewrite it as a minus b times a plus b. Always works. A squared minus b squared equals a minus... Well, this is close. I have the minus, I just don't have the squareds. Yeah.
So when you write it as cosecant squared minus cotangent squared, and then cosecant squared plus cotangent squared?
Yes. That's exactly what we're going to do. I'm gonna work up to that, but that's 100%. If you know how to do that, you can just do that right now. If you didn't hear what Mercer said, here's basically what we're going to do. If I ever have a to the 4th minus b to the 4th, I can think of this as being a squared squared. Because when you raise a power to a power, you multiply. It'd be 2 times 2, which would give me 4. Minus, well, it'd be b squared squared. So I could rewrite this as, and instead of it being a minus b squared, this is an a squared squared minus b squared squared. So these are actually my a's and my b's. So I could rewrite this as a squared minus b squared times a squared plus b squared. I have the exact same thing being squared. I have a squared squared minus b squared squared. So look at what's being squared. It's the a squared and the b squared. You could go one step further and go, okay, a squared minus b squared equals a minus b times a plus b, but I'm just going to stick with this. Okay, so I have something to the 4th. I want to turn it to squared so it matches my Pythagorean identities. So that means I am picturing this as being the same thing as cosecant squared squared minus cotangent squared squared. Now it's a difference of squares. The only thing is that these are my a's and b's. So once again, I'm just picturing this element is my a, this element is my b. That a squared minus b squared equals a minus b times a plus b. So in this case, my a is cosecant squared, so we'll have cosecant squared x minus cotangent squared x times cosecant squared x plus cotangent squared x. Now let's make another note to ourselves. Let's do another note. I know that cotangent and cosecant are joined together when they're squared because we have a formula that goes 1 plus cotangent squared x equals cosecant squared x. Oh, what if I just subtract cotangent from both sides? If I just subtract cotangent from both sides, so if I subtract cotangent squared x from both sides, I will now have 1 equals cosecant squared x minus cotangent squared x. Does that help us with anything over here? What does it help us with?
Because isn't that one of the identities?
Yeah. But how does it help us here?
You just replace it at 1.
I can replace it with 1. So anytime I see cosecant squared minus cotangent squared, which I see right here, I'm going to replace all of that with just 1. And so that's going to equal cosecant squared x plus cotangent squared x. Now we're going to go back to the Pythagorean identity. I have 1 plus cotangent squared equals cosecant squared. Is there any way to manipulate this formula so I have a positive cosecant squared and a positive cotangent squared?
No. Or you can move the over.
So if I move the cosecant over, won't I have a negative cosecant squared?
Yes.
Oh.
There is no way to manipulate this that both of these are positive. We are actually going to be done here. Now, I will tell you, you might do other steps. You might say, okay, I could change cosecant into sine. I could change that into 1 over sine. I could take cotangent into cosine over sine. I'm going to tell you that's actually going to get more complicated. You're going to try that on your own at times, which is awesome. But I'm going to tell you right now, this is as simplified as we're going to get on this one. But we should have been thinking, oh, cosecant turns into 1 over sine, that turns into cosine over sine. But you can't really simplify it. You can push fractions together and it makes it more complicated. So I'm just giving you a hint right now that this would actually be done. Okay? So that's how we knock things from the 4th power down to the 2nd power. Now, likewise here, I don't have anything that deals with cubes. If you look at your sheet, that rectangular sheet, there is nothing that says cube down there. The highest powers are squares. That is our Pythagorean identities. If you see something that's cubed, you got to knock it down a power. And one of the easy ways to knock it down a power is to see if you can factor it. And what I mean by factor it is if you look at this bottom fraction, this bottom fraction has sign in both elements. It kind of like, what I'm kind of picturing is, this is the same thing as x cubed minus x. I can turn x cubed minus x into x times x squared minus 1 by factoring out an x. I bring an x out of each of those elements. Now remember, it has to be all the way across here. If this was like a plus 1, it wouldn't work. But there's sign in both of those elements, so I'm going to factor out a sign. I'm going to bring a sign out of both of these things and put it in front. Turning this into sine cubed x. Maybe I should give myself a little more room. Sine cubed x all over sine x times, well, sine cubed x dividing sine x out, we'll have sine squared x minus sine x divided by sine x is a 1. What's sine cubed x divided by sine x?
Sine squared.
It'd be sine squared. It would be sine squared. Just like if I had, let's do another example. If I had x cubed over x, that would just equal x squared over 1. So we're going to do this division. That division is going to turn this sign into a 1. And we're going to turn that cubed into a square. Just like x cubed divided by x turns into x squared, sine cubed divided by sine turns into sine squared, which all of a sudden we have sine squared x all over sine squared x minus 1. What should pique your interest about this sine squared minus 1? It could be made into some form of cosine, right? Remember, we don't just guess. We don't just say, oh, that's cosine x, or that's negative cosine x. We do a little bit of work. So if I see sine squared minus 1, we just immediately go either in your head. Some people in their head can do this. I don't like that. I just like just writing sine squared plus cosine squared equals 1. To create a negative 1, I would have to subtract 1, right? So if I subtracted 1 from both sides, all of a sudden I have my sine squared minus 1 plus cosine squared equals 0. How do I get the cosine to the other side? We would subtract it, so we would have sine squared minus 1 equals a negative cosine squared. So if I ever see sine squared minus 1, it's actually going to equal a negative cosine. So we're going to replace this sine squared minus 1 with a negative cosine. So we'll then have sine squared x over a negative cosine squared x. Wait for everyone to catch up to make sure we don't have any questions. Your big thing is if you're using the Pythagorean identities, and it's not just sine squared plus cosine squared equals 1, you should have it written down. And if you write it down for every problem, you get to a certain problem, you can just look at other ones. You can go, oh, I already wrote this one down. I know that now that if I see sine squared minus 1, it's a negative cosine squared. Well, now we have sine over cosine. What does sine over cosine equal? Tangent. So it'll be negative tangent. It will be negative tangent squared. Now, I will tell you, these aren't the end-all, be-all of how to solve problems. These are just tools for the toolbox. Do you use every tool on every problem? No. Sometimes you'll try a tool and it doesn't work, and we go back and we try a different tool. So a lot of these problems we're going to start seeing as we advance. Take that first step. Do something. Don't stare at it. Try something. That's why I say with your notes, I'm not going to give you points for just not trying anything, because there's things you know how to do. You can't just stare at it and go, I don't think it's going to work. You have to try something. And it might not work. You might get to a point like, this is getting way too complicated, I made a mistake. That might be a point where you go to the next problem, or you try a different method. If you don't know a method to try, that's a good time to ask in class, Mr. Pavey, I tried this method. Would it work? And I could say yes, and we can go through it that way. Or I'll say, no, we should have went back and did this different method. We're learning a whole bunch of methods to just practice these problems. The key word there is practice these problems. You are going to bomb this test if you're not doing homework, because it's just practicing these over and over and over and over. There's only so many problems I can give you. You're going to find out that when you see something, you're like, oh, I've done this a billion times, I just got to do this method. But if you haven't been practicing it, you're not going to be able to do that. The goal is on the test. Hopefully the ones I put on this test are like, I've seen that one. I just do this. Like you automatically know what steps to do. But once again, that takes practice. All right, questions for me at all? Okay, then the rest of the time is yours to work.